Okay, what we're going to look at now is the application of Polaroid filters or polarizing filters. Okay, so basically when we use polarizers, we use two polarizers, one in one direction, one at 90 degrees. And so what's going to happen, we have unpolarized light, where the electric field component is oscillating in all directions, incident on the first polarizer. Then we get completely polarized light, and then goes on to the second polarizer, which is called the analyzer, and that's at 90 degrees. That's offset at 90 degrees, so there will be no light transmitted. Notice that the radiation that's transmitted from the polarizer is half the intensity, because the horizontal component has been filtered out. Basically half the radiation has been filtered out, so the intensity is half of what it was before. So unpolarized light on the polarizer, then polarized light transmits through the polarizer and is incident on the second polarizing sheet, which is called the analyzer, which is set at 90 degrees. Okay, and what we do is that we place material in between the two of them, which is, we describe it as being optically active. And what that means is that it also polarizes, it basically rotates the axis of polarization. And we're going to see how this is useful soon. Now, if we change the axis of polarization, so we have an incident light here, which is amplitude A, and then we have an analyzer which is at angle theta here. If it were 90 degrees, then none would be transferred. If it were 0 degrees, all of it would be transferred. But we're taking this angle here, theta. So we have to take this component of this one, of the incident light, on the analyzer. So we have the angle here, we have the opposite. So we are going to be talking about cosine. So the amplitude A1 of the component parallel to the transmission plane is given by A1, so this is A1, is equal to A0 times by cosine of theta. Okay, so this is A1, this is the amount that's transferred through the analyzer. That's the incident ray, which is has an amplitude A0. So it's going to be A0 times by cosine of theta is this component on this axis here. However, the intensity is, this is basically the amplitude of this wave, and A is the amplitude there, and then A0 is the amplitude of the incident light. However, the intensity is proportional to the amplitude squared, so we have to square everything here. So basically A squared is equal to A0 squared cosine squared theta, but A squared is equal to the intensity. So the intensity in the transmission of the plane of the analyzer is equal to the original intensity times by the cosine squared of the angle between the two. So I0 is equal to I1, the transmitted light, is equal to I0 times cosine squared theta. This is Marlus's law. Okay, so what we have here is the light source, which is completely unpolarized. Then it goes through the polarizer. Then what happens is that this becomes plane polarized. The intensity is now half of its original value. And then we have another analyzer, which is at a certain angle, and it becomes plane polarized, but slightly differently. But it's going to be according to the cosine squared of that angle times by this value, because this is the incident radiation that's on the analyzer. You can try to do this problem. Pause. Okay, so this is basically Marlus's law. The transmitted intensity of polarized light is equal to the product of the intensity times the square of the cosine of the angle between the analyzer and the direction of the electric field vibration of the polarized light. So I is equal to I0 cosine squared theta. I0 is the incident radiation. What is meant by optically active substance? An optically active substance is one that rotates the plane of polarization. So the light which is polarized, which is going for this optically active substance, if it's vertical, it would be rotated slightly by a few degrees. And this is how we use the polarizer and the analyzer. So this has got vertical orientation, that's got horizontal orientation. So what's going to happen now, this vertically polarized light is going to be slightly rotated, let's say to the right, in a clockwise direction by 5 degrees. So, in other words, to find out how much this actually rotates it, to find out that it's 5 degrees, this also has to be rotated slightly by 5 degrees so that it blocks out all the radiation, and therefore we will know that that will rotate it by 5 degrees, because otherwise, if this is vertically orientated, this is horizontally, then this should block out all the radiation. At the moment it won't do, because this has been rotated slightly, so this has to be turned by 5 degrees to compensate for that. So here's another thing, unpolarized light, polarized light. This gets slightly rotated, so in other words, this there will be some light that will be emitted here, so we have to rotate this slightly to block it. Describe the use of polarization for the concentration of certain solutions. So, the angle of rotation depends on the concentration and the distance. And it's used to find syrup concentration. If you know, for example, that 1 molar solution of 40 centimeters length of 1 molar solution rotates by 5 degrees, and you're rotating it by 4 degrees, or let's say 10 degrees, you know you're either going to have twice the concentration or twice the distance. And you can measure the distance, so you can find out the concentration easily enough. Also, stress analysis. Some materials are optically active under stress. And when they are stressed, you can see polarizing patterns where you see different colors which are polarized through the materials. For example, this. You can see here, this is a point of stress, this is a point of stress. These are seen through 2 polarizers, as a polarizer and an analyzer, and you can see that this is a point of stress here, and this is a point of stress here. You don't need to know more than that. Qualitatively, how can they be used? Well, basically, you can see patterns of the polarized light on the stress points. We have to understand the action of liquid crystal displays. So, an LCD, you have first of all the polarizer. Unpolarized light goes through, and when it's switched off, this gets rotated by 90 degrees. Then the polarizer is at 90 degrees, so that transmits all this light. It comes back, and it ends up back in the vertical position again. So if your calculator is off, you'll get a light screen. The light goes through, gets rotated, and then gets reflected, gets transmitted, and you see a light screen. However, if you turn on the calculator and you press a button, basically the voltage stops this from rotating the plane of polarization. So this will only allow vertical plane of the electric component to be transmitted. And this is a horizontal plane, this one here. So it will all be absorbed, so it means that there will be no light that is reflected, which means it will appear dark, and you know that. A liquid crystal, when you look at it and when it's switched on, it goes dark. When it's off, it's clear. And this is the same again, but a little bit more complicated. Also, in LCDs, this is used like on a computer screen. This is for polarizer as well. Solving problems. Okay, you can solve the problems from any of the textbooks or any of the question banks that you've been given. And I think that's it, really.